Okay, so let us come back to what we said. When now I have made this WL is equals to 1. When WL is equals to 1, it means that some bright color. Can I have some bright color? Yes. When we have WL is equals to 1, it means that this transistor will behave as short circuit. And since you have QB also equals to 1, so it means QB is equals to 1 will travel from here to here. You have high potential here. The high potential here means this transistor will also on, and this will also work as short circuit. So potential, what path the potential will have? The potential will have this path. This is a short circuit. This is again a short circuit, and this is a ground. Right? So effectively, BL should go to 0, and by 0 I means it should be less than VDD by 2. Anyone who did not got this point, I can explain this again. If anyone wants me to explain this. I repeat this again, that if you please see this carefully, that you have VDC is equals to X over here. And when you have VDC is equals to X, it means that where the pointer has gone, I need the pointer. Yes. Okay, it's not enlarging the screen. Okay, I do have some problem here with my pointer. I'm not able to use my pointer over here, but no worries. I'll try to show this to you. See this, I have VDD is equals to X. No, please don't do. Who is doing this? Please don't do. Okay, right. I have, thank you. Who has done this? Thank you. So I have VDC is equals to X. And here you have ground. Ground here means that this transistor is turned on. This is PMOS. It is shorted. When it is shorted, your potential will have this path, right? And in this path, you will see that the BL is high. BL is high because of this VDC is equals to X, and this is a short circuit. When this BL is high, you will see that when this BL is high, you will see that this BL will try to take the path which is short circuited, which is a low potential. Now, how this looks for this low potential path? This is very simple thing that one can understand. And that simple thing is that this QB is 1. When this QB is equals to 1, you will see that this transistor NM1 is on. When this NM1 is on, and because of WL is equals to 1, this transistor is also on, the BL will get the path this way towards the ground, right? So BL will get the path this way towards the ground. Okay. So when BL is having a path towards the ground, it will show you that the BL is slowly coming down. So we will see that the BL is slowly coming down. Let us see this with the help of simulation. Now you please see these values. The Q is at 0. QB is at 700 volts, means it is 1. BLB is high, 700 millivolts. But BL, it is 300 millivolts. What is the meaning of 300 millivolts? 300 millivolts means that BL is coming down. It is below VDD by 2. What is VDD by 2? 350 millivolts. You are working on 700 millivolts. So VDD by 2 is 300 millivolts. So it is less than half, but it is not workable, right? It is less than half, but it is not workable. So what we do in this case is, in this case, see everyone, I am not able to explain this because my pointer is not working. Give me 1 minute so that I can restart my system, and I'll not be restarting the Zoom. This will keep on working. I'll restart my this cadence so that it keeps on. It can show you the correct values and it can show you the pointers as well. So I need to restart it. There is some problem with this so that I can explain it to you. I'm not able to explain you this properly. So give me 5 minutes. It will open up. Okay, so here we go. I'm done till the point where we reached. Now you please see this. The potential here is approximately 300 millivolts. And what is VDD by 2 for 700 millivolts? It is 350. Now we want it to have more distance. We want this potential at BL. This is the value of BL. You see this. This is the value of BL. This red line, this red represents the BL. So the value of BL is around 300 millivolts, and we want it to get discharged somewhere around below 150 millivolts. How can we do that? We have seen that in this case, the BL, the high potential on BL follows this path. If from 700 millivolts, it is coming down to 300 millivolts, it means the whole potential is not being grounded. There is some resistance. Now resistance, what is the resistance? Resistance can be some MOSFET. Either this MOSFET is resistance or this MOSFET is resistance. And what is the characteristic of MOSFET? If you, in MOSFET, if you increase the width, then drain current increases. Increase in drain current means, if your width increases, drain current increases, means your transistor is becoming a good conductor. So when you increase the width of a transistor, you increase the conductivity of the transistor. So this means that if you improve conductivity of this transistor and this transistor, more potential will get the path towards the ground. Let us see this with the simulation. You see, I increase the width of this transistor. Let us say it is 120 millivolt. I keep it to 240, sorry, 120 nanometer. I get it to 240 nanometers. I've just doubled the width. And the width of this transistor, I make it to 260 or maybe 300 nanometers. I'll explain you why this 240 and what drove me to make this 300. This is not, these are not the random or arbitrary values. I'll show you how this works. Now, when I simulate this, let us see how much potential we were able to discharge. Now you see that the potential on BL is 90 millivolts only. Before increasing the width, it was 300 millivolts. Now it has came down to 90 millivolts. It means that, it simply means that whatever potential is coming from here is now getting more easy path towards ground. Means these two transistors have become better conductors. Means increasing the width has improved the conductivity. Now the point is why I took it 240, why I took it 300. There are two reasons behind it. One is the logical reason and one is the mathematical reason. What is the logical reason? Let us assume that Let us assume that this is working as a pipe, right? We are assuming that this is working as a pipe. Now, when this pipe, let us suppose this pipe has a width 24 centimeter, and this goes towards this pipe. If this size is 20 centimeter, then what is the logic of sending the water from 24 centimeter? Ultimately, this 20 centimeter will become the bottleneck. What logically we do, if the size of this pipe is 24 centimeter, then the size of this pipe should be 30 centimeter. So that whatever comes from here should easily pass through this pipe, right? And what is the mathematical reason? If this is only the logical reason, what is the mathematical reason? Mathematically, in 60 SRAM, the width of excess transistor, if it is taken in denominator, and width of pull down transistor, if it is taken in numerator, its value should always be greater than 1. This transistor is called pull down, and this transistor is called excess transistor. And this ratio is called cell ratio. The cell ratio should have the value greater than 1. What is the cell ratio? Cell is the width of pull down transistor divided by width of excess transistor. So this is a, there is a question that is coming up. What is the question? Let me see. If we increase the width such that VDD drops below VDD by 2, it will increase the leakage of NMOS. Yes, it will increase the leakage of NMOS, but give me some time. I'll explain the reason to you why this is very important. It is very important that whenever you make any SRAM cell, this potential in particular, the potential at BL or the bit line which is on the side of 0 bit, which is on the side of 0 bit, should be below VDD by 4. Below or somewhere equal to. Your potential was initially 700, right? So 700 by 4 is around 175 millivolts. So it is below 175 millivolts, right? So that's the case. And since 60 SRAM cell is symmetrical, so that is why it is more important that you understand this fact that there can be logic 0 here, and there can be a case when logic 0 will be here. So these two transistors should have the similar values as compared to their corresponding transistors. Right? Now your 60 SRAM cell structure is complete with respect to read operation. Now let us see how much power is dissipated in read operation. This is around 660 nanowatts. And Shivansh was right. When you increase the width of excess transistor and pull down transistor, you have made them better conductors. When they are better conductors, they pull BL and BLB down better, but the leakage also increases. Now let us see what is the leakage in this case. For leakage, I make WL is equals to 0. and I'll see what is the leakage now. It was initially 5.566 something, and now it has gone to 7.90, approx 1.5 times the leakage has gone. The leakage has gone up by 1.5 times. But your SRAM cell is reading in a better way. Your BL is getting pulled down. Now, how do we do the write operation? For write operation, I assume that Q is equals to 1 and QB is equals to 0, or Q is equals to 0, QB is equals to 1. So how do I do the write operation? So I cannot have a fixed bit here. Now for write operation, on one side of this SRAM cell, I'll give 0. For one side, analog, this 3. On one side of bit line, I'll give this high. And on the other side, I'll give 0 potential. So one side high, one side low. And wherever you give the high, you have given a high over here. So Q will become 1 and QB will become 0. And before that, your WL should be 1. Now you simulate it. Please see your Q has gone 1, 700 millivolts, and QB has gone 0, approximately 0 volts. Now let us do the reverse practice. I take this as 0 volts and this as 1 volt. So now, because you have given 1 on this side, so QB should be 1, Q should be 0. Now the QB is 1 and Q is 0. Right? So that's how I write my SRAM cell, that whatever bit I want to write on Q and QB, I give the potential at that point and approx 0 at the other point. Now, one point I missed, you see one point I missed during this process, that I wanted to explain this in read operation. Read operation, BL and BLB reads only when WL is high. If WL is not high, BL and BLB will not read anything. Let us see this here. WL is 0. See the results. BL is high, BLB is also high. Both are at same potential when WL is 0. And when I make WL 1, your BLB has come down, right? Now, what I'll do this, I give pulse to WL. You please see, when you give pulse to WL, you see BL and BLB coming up and down. Whenever you have WL high, the BLB get discharges. When WL is zero, BLB does not discharge. Again, this BL get high, WL get high, BLB discharge, otherwise does not discharge. This is how the read operation actually takes place. Whenever your WL is high, so this is a dynamic operation, and the power consumption is also, the dynamic operation is usually higher than the static. This is 1.1186 microwatts, the power consumption is, right? Do not get carried away with this. This is completely zero. And if you see this, so this is your QB, which is absolute zero. This is your Q, which is absolute one. This is your WL. When it is high, the BLB is discharging. When it is low, BLB is not discharging. And if you have zero over here, you will see that the discharging is at BL. Please see this. Now discharging is at BL. So that is how your read operation takes place. Now I have explained you all read, write, hold operations. Please ask if you have any questions. Now we are left with only one topic, that how do we decide the stability in SRAM cell? And second, how do I see the delay in SRAM cell? Only two things are left. Then I'll make you understand that how do we create array of the complete SRAM, right? Please ask me if you have any doubts still here. I'll try to incorporate your queries also. Anything that you feel like as a query, I'm open to take it. Any random questions? SRAM cell is very important part of this digital VLSI design, because you cannot assume any device. When I say any device, I mean it. You cannot assume any device, any you call it, any device means you cannot talk about any processor, you cannot talk about any controller, you cannot talk about any IoT based device which is without the memory. So when you start working on any digital circuits, probably memory will be the one which will come in your way. And the way of understanding the memory is vague for most of the people who study this. Please study it in a sequential manner, like what is the read operation, what is the write operation, how do you manage the transistor width, where the transistor width is needed to be increased, what is the meaning of the read operation, how do you manage the write operation inside this, what is the meaning of hold power. See, in case of write operation, you talk about the dynamic power. In case of the read operation, you talk about the dynamic power. But in case of hold operation, you talk about only the static power. That is how this whole memory is envisaged. I don't want you to put up the questions. If you are not getting any questions right now, please go through these two videos today, and then you come back with the questions, because I don't think that understanding memory is that easy that you don't do not get any queries. And once you get any queries, then you are most welcome to the class, and then I'll try to take on your queries. You can put up your queries whenever you get any query in your mind on the WhatsApp message also. I'll try to reply all your questions here. For today, that's all from my side. I have only two things left. One is the stability of memory, and one is the delay part of the memory. I'll explain it on the next working day. Till then, good night. Thank you for joining, and we'll see more in coming days.